Right, so we stopped here last time. We were discussing about the design of gating system. I hope you remember that there are said that there are two basic principles of fluid flow relevant to the design of the gating system, which is the Bernoulli equation and law of mass continuity. Two equation, two system, two principle or two fundamental we're going to use to design the gating system: Bernoulli theorem and law mass continuity theorem. Right. So start with the Bernoulli. If you remember, we said that the total pressure equal to constant mean H plus rho g, pressure divided by rho g plus V squared divided by 2g equal to constant. That's what we were discussing last time, and we stop here in this slide. In the casting, in a gating system here, we put liquid now. There are a liquid inside. So in a gating system, this is a gating system here, as you can see. There are a liquid metal. Liquid metals, then we can apply Bernoulli equation. So this one supposed to be filled with the liquid. Then we would like to apply Bernoulli equation. As I told you last time, most important thing is point 2, which is a down spiral. Point 2, we call it, is a down spiral, this point. This is very important because the condition at point 2 is a condition of the liquid that will deliver to the main cavity. So the condition here at point 2 is very important. So we're always looking for condition at point 2. Last time I told you to avoid aspiration. What is the aspiration? Aspiration, actually, as written here, aspiration is a gas trapped in a mold, in a metal, liquid metal or liquid material. So gas trapped inside liquid material and finally leading to porosity. To avoid aspiration, B1 should equal to B2 equal to B0, means the pressure must, whatever we call, is the atmospheric pressure throughout. Atmospheric pressure throughout. So it must be atmospheric pressure throughout. So when you said atmospheric pressure throughout, this one to avoid actually aspiration. So to avoid aspiration, as I told you, to avoid aspiration, then atmospheric pressure throughout. Atmospheric pressure throughout means the pressure here equal to here equal to here equal to the atmospheric pressure 0. And this could be done in a Bernoulli equation. If you apply Bernoulli equation between point 0 and point 2, for example, between point 0 and point 2, if we apply Bernoulli equation, then in very simple way, we can say that here the pressure at 0 is equal to 0. Pressure also at 2 is equal to 0. Why? This one to avoid aspiration, then pressure 0 equal to pressure 1 equal to pressure 2, then the pressure at 0 is equal to 0, pressure at 2 also here equal to 0, which is atmospheric pressure. And V0 here is equal also to 0. Then V0 here, velocity at this level is equal to also here relatively. We can just, for simplicity, we can just ignore velocity here equal to 0. Then this is the equation. We can put actually, where is the reference here? Reference is here. We can put reference is here. So this is the 0 axis. So this is the references. For example, if we take references here, then you can see that Z2 equal to 0. So Z2 here, because we put the reference here, so Z2 equal to what? Equal to 0. Because we put the reference here, and Z0 equal to H2. So Z0 equal to H2. Z0 equal to positive H2. Right? So Z0 equal to positive. This is the level here of 0 is equal to H2 because I put the reference in point 2. I put my axis. Someone will don't want to do this, would like to put the axis in 0, no problem. You can put the axis in 0, then here z0 will be 0, but z2 will be minus h2, then will be minus h2, will be same, will lead to the same. So this is the equation, this is the h2, this is the 0, then you get here 0, again, then you get here 0, get here 0, get here 0, as you can see. This one is h2, this one is 0 also. Then you get the equation from here, you get the equation v2, which is the velocity at 2, v2 which is the velocity at 2 equal to square root 2g h2. Actually, this equation is very important equation. Why? Because this equation tell you about the velocity at point 2, This equation tell you the velocity, or to inform you that what velocity is supposed to be at point 2 to avoid aspiration. So to avoid aspiration, velocity at point 2 should follow this equation 2gh2. What about velocity at h1? Should follow the equation also square root of 2gh1. If you apply between 0 and 1, avoid aspiration, you get same equation, but v1 equal to, if you talk about v1 equal to square root 2gh1, h1 which is the height of 0.1. So this equation is very important to tell you what velocity should be at this point 2 to avoid aspiration, Someone will ask me, right, okay, we understand. Already we calculate. We know that what velocity is supposed to be at point 2 to avoid aspiration. How we can exactly satisfy that velocity at point 2 equal to this value? This one will know from the next step. Next step, we have whatever we call is the law of mass continuity. Law of mass continuity said that this is the second theorem we use to design the gating system. Q equal to AV equal to constant. AV meaning area multiplied by velocity. Then Q is a cubic meter per second. Q is whatever we call is a flow rate. Q is a flow rate, which is a cubic meter per second flow rate, or volume flow rate, or volumetric rate of flow, or volumetric flow rate. Volumetric flow rate means cubic meter per second equal to AV, A1 V1 equal to A2 V2 equal to constant at any level. You can apply at any level. Means that A1 V1, which is the area here multiplied by velocity here, or area here multiplied by velocity here. So A1 V1, A2 V2, and constant at any level. Then we can from here know that A2 divided by A1 equal to V1 divided by V2 from here. A2 divided by A1 equal to V1 divided by V2. So this is the equation we obtained from the mass continuity, or law of mass continuity. Okay. Right, so if we know the velocity here, at point 2 from the previous step, by using Bernoulli equations that satisfy the condition avoid aspiration. So if you know what is the velocity and we know the area, here, then VA equal to Q. Q is the flow rate. We can actually, as I told you, flow rate is constant. So we're pouring liquid here, at certain flow rate. As we know the area and velocity, we know the area here, we know the velocity here, then we can calculate the flow rate, which is cubic meter per second. Then we can apply flow rate here, so flow rate will coming at constant flow rate. Then flow rate, when you apply constant flow rate at certain area, velocity will satisfy the condition of avoid aspiration. Do you get it? So this is the issue usually. Even this is available or provided in a software. We call it Magma software. This software help people to do the casting process, doing what I'm just telling now, using Bernoulli equation and mass continuity equation. So Bernoulli equation, we apply in a Bernoulli equation, as we described earlier in the previous slide, this one, we apply Bernoulli equation in a way that this says, then you get the equation here, V is equal to square root 2gh, or V2 equal to square root 2gh2 here. Then this is a velocity here at this point to avoid aspiration. As long as we know the velocity here to avoid aspiration, then you can apply in mass continuity equation. We know V2, we know E2, then we can know flow rate. Then we can apply flow rate here. We apply flow rate here. We put the liquid here at constant rate. Then this one definitely will provide later velocity, exactly the velocity needed at point 2, the velocity needed at point 2 to avoid aspiration. In this way, you can satisfy the condition of avoid aspiration and porosity in metal casting, or get defect in metal casting. Right. So two equation now. From here, from the second equation, we know that A2 divided by A1 equal to V1 divided by V2. Okay. Mix now two. I just would like to mix Bernoulli, the Bernoulli equation and mass continuity equation, and see what we can get. So you can see that V2 equal to square root 3gh2 here at point 2. V1 at point 1 equal to at point 1 here. This one to avoid aspiration. Definitely, I don't want to say this again. I'm not going to ask you whether to avoid aspiration or not, but this is by default. By default, whenever I give you any problem in a casting, you must consider in your mind, you must avoid aspiration. If you didn't avoid aspiration, if you did not consider this case, which is avoid aspiration, you get defect in a casting, and this casting will be scrapped. This one must be satisfied. I'm not going to explain. I'm not going to tell you in a problem when I give you. I'm not going to give you the condition that to avoid aspiration keep. No, I'm not going to do this one. I'm not going to tell even. Automatically, this is by default, it must be avoided aspiration. Otherwise, I get defect in the casting. So this one must be considered all time. Right, so in this case, avoid aspiration, you get V2 equal to square root 2gh2. This is V2, 2gh2. What about V1? V1 here equal to square root 2gh1, which is the head of point 1. This is both two equations. From this one we obtain from the equation 1 and 2, we obtain from Bernoulli equation. Second equation, which is this one, we obtain from mass continuity equation. A2 divided by A1 equal to V1 divided by V2. This is one from mass continuity equation. So we have this one. So V1 here and V2 here, we can apply V1 and V2 here in this equation. Then A2 divided by A1 equal to V1 divided by V2 equal to V1 equal to square root 2gh1 square root 2gh2. Then G is constant. Then you get square root h1 divided by h2. Then you get this equation. So this is another equation obtained from mixing both Bernoulli equation and mass continuity equation. Then you get A2 divided by A1, A2, which is area at 2, divided by area at 1. The relation between area 2 and area 1 equal to square root h1 divided by h2, h1 divided by h2. Then A2 divided by A1 equal to square root h1 divided by h2. This equation obtained from here. So we can use this equation in analysis, in further analysis. So actually, this is the only three equation we have. This is the only three equation we have in this area, designing the Sparrow or the gating system. This is the first equation, V equal to square root 2gh. Generally, you took V equal to square root 2gh, whether V1 or V2 or any V, right? Second equation, this equation, which is Q equal to AV equal to constant. Third equation is a relation between the area and head, A2 divided by A1 square root H1 divided by H2. This is the only three equation we have in designing gating system. Yes, Muhammad, I'm listening.
دكتور متى أعرف إني لازم أستخدم برنولي أو هذه؟
We will explain an example. I'm going to show some example now, and we'll solve the example together. Then we'll learn you how to dealing with this kind of equation, right? Okay. So now today in this class, so going to take some some example, maybe 2 or 3 example related to this one to show you how to deal with the equation, how to use this equation, solving or designing the gating system. Now I am just explaining the fundamental now. Did you get it? Any question about that? If it is clear, then it's fine, and we will go to the example.
Yes,
We'll see how
yes,
to deal. Yeah. Then when we go to the example, you will see how to apply this equation to solve the gating or design the gating system. Right. So now we have 3 equations. Remember that 3 equations. This is one equation, velocity equal to square root of gh. Second equation, q equal to av equal to constant. Third equation, we obtain here a2 divided by a1, relation between area and head. This is the only 3 equation we have. We don't have more. This is the only 3 equation we have, and so we're going to use to design the gating system. This equation, this one, A2, is the relation between A and H. We will take it here. This is A2 equal to A2, area here at 2, equal to area 1 multiplied by H1 divided by H2. It is exactly same. Now this is the equation. Huh? This is the equation. A2 divided by, put A1 here. So A2 equal to A1 multiplied by square root H1 divided by H2. So this is the equation actually. When you look to the equation, this equation, guys, when you look to this equation, this is very important. Please just give me your attention. When you look to this equation, right? This equation is satisfying avoiding aspiration. This one satisfying avoiding. It must be satisfied. This equation must be satisfied. When you look to A1, this is the area here. A1 is the area at 1. A2 is the area at 2, right? Multiply by H1 and H2. What is the relation between H1 and H2? Look to H1 is here, H2 is here. So is it equal? H1 and H2 are equal? No, not equal, right? So H1, it's clear that H1 smaller than H2. Then A1 and A2 not equal. A1 and A2 not equal. If you multiply by H1, this is the H1. If you multiply, this is the H1 here, right? This is the H1. And this is the H2, right? So you can see that this ratio is less than 1. The meaning that A2 smaller than A1 bigger than A2, or A2 smaller must be smaller than, with this ratio. So the relation you get from this ratio, A2 must be smaller. You agree? You cannot just keep like here, parallel side and A1 equal to A2. This is wrong. We just sketch, we do sketch like outline sketch to show in this way, but this is wrong. It couldn't be like this. A2 must be smaller than A1, right? A1 bigger. Then it could be like this, taper. So actually, we cannot just make it parallel side, but taper. Taper must be taper to satisfy the condition. So A2 here, the area here, must be smaller than A1 to satisfy the aspiration. Someone will ask me, how big, how small it is? You multiply by the ratio. If you know H1 and H2, you multiply, you get a relation between A1. So you can, if you know A1, you get A2, or if you A2, you get A1. So the ratio must be satisfied. So it could be taper. So actually, when you look to the actual Spiro, you find it is taper. It is not parallel side. Can you see that? It is taper. We usually create Spiro as a taper, not parallel side, as you can see, because the area here is smaller than area here. Another solution, alternative solution, they make whatever called choking mechanism. Choking mechanism is they sometimes do here reducing area, not very common, but in some cases it happens. They put whatever we call orifice here to reduce the area. So area here becomes smaller. They call it choking mechanism, or reduce the area here to reduce the area for flow. They call it choking mechanism, but the most common one is to create it as a taper. So Spiro must be designed as you can see here, right? Any question? Right. If it is clear, meaning fine. So Spiro must be as you can see here. If you just magnify, see it is taper. It is not parallel side. So area here definitely smaller than area here. That's what I'm just telling about this one. Final thing, the last thing here is another equation, which is a time to fill the cavity. Time needed to fill the cavity. This is the cavity, right? So this is the cast cavity. This is the cavity. Time to fill the cavity. You can see that this is a Spiro. This is a Spiro. This is a runner. This is Sparrow, this is a runner, this is Sparrow, this is a runner, right? So this is a Sparrow, this is a runner, this is the main cavity. Liquid is coming from here to here and then come to at flow rate, at constant flow rate Q, which is Q equal to what? Q equal to cubic millimeter per minute to fill the cavity. Cavity is volume, certain volume. So if we know the volume, then the time to fill the cavity equal to the volume of the mold. This is the volume of the cavity divided by flow rate. Then mold volume is cubic millimeter. This is cubic millimeter divided by flow rate, which is the cubic millimeter per minute. Then cubic millimeter goes cubic millimeter, you get minute, which is the time. So the time to fill the cavity, equal to the volume of the mold divided by the flow rate. Divided by the flow rate. If you know the flow rate, you know the volume, you can obtain the time to fill the cavity. Any question? Right, so let's take an example. Let's read it together. Let's read together. Right? One by one and understand and then try to solve this problem together. Right. Okay, please give me your attention. Let's read it. So a mold sparrow. This is a mold sparrow. This whatever we call is a mold sparrow, right? Mold sparrow 20 centimeter long. So it is the height from top to down is 20 HT equal to 20 centimeters. So HT equal to 20 centimeters. The cross-section area as its base here. Base meaning in this area, cross-section area here, which is the area 3, A3 equal to 2.5 centimeters. So you can see that this is height HT equal to 20, and this is the area at the base. This is the height of the sparrow HT equal to 20. This is the area at the base here, which is A3 equal to 2.5 centimeters square. The sparrow feed horizontal runner. This is sparrow feed horizontal runner. This is a horizontal runner, right? Horizontal runner leading into the mold cavity. This is leading into the mold cavity. This is a mold cavity whose volume is given. This is the volume of the mold cavity. So volume of the mold cavity is given. So this is the volume of the mold cavity. So it is given, right? This is the volume of the mold cavity. What is needed? The question is determine velocity of the molten material at the base. We need to know V3. What is the V3? This is the first question. Second question, what is the volume flow rate? What is Q? Third question, what is the time to fill the mold cavity? One by one. We need to know V3. How to obtain V3? Is a very simple way. V3, V at the base, which is a V3 equal to square root 2G HT. We know HT. HT is given, which is 20, right? Then square root 2G HT. G is the gravity acceleration. Then 2 gravity acceleration 981. And this is the height, which is 20. Then you get this is velocity at the base. So we know now the velocity at the base. There's the first question. Okay, guys? Any question? Is it clear? Is it clear? So the first question, what is the velocity at the base? So velocity at the base is V3. Second question, what is the volume flow rate? We need to know Q. Q equal to what? Equal to V multiplied by A. What V and what A? Any V and any A. Could be V1, A1, could be here, could be at any level, because it is constant. It could be here, you calculate 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 here, any level. As long as we know the condition at 3, we know the velocity at 3, and we know the area at 3, then we can apply at 3. Then here you apply, you get the at 3. So in Q equal to V3A3. V3 already we have here. This is a V3 and area is already known. Area is here 2.5. You multiply VA, then you get the Q. This is the flow rate. This is a flow rate which is cubic centimeter per second. Cubic centimeter, cubic meter, cubic per minute, per second, no issue. Just as you wish. Most important thing to keep, all units in equation same. All unit in equation is same. So Q here is, this is a Q or flow rate. Third one, what is the time to fill the mold? What is the time to fill the mold? Equal to V divided by Q. V we know is given. This is a V. Okay, and Q already we obtained here. So V divided by Q, then you get the time, 3.2 time needed to fill the mold. Right. Any question? I'm listening. Any question? Is it clear? Right. Move forward. Okay. Yeah. Perfect. Yeah. One by one, you will learn how to deal with this kind of question. So second problem. Let's read together. Down sparrow. This is a down sparrow. Actually, it is taper now. Can you see that? It is taper. Not parallel side, but taper. So down sparrow shown in the figure has been designed to avoid aspiration. No need to say. No need to say. Actually, I'm not going to tell you that. Has been designed to avoid aspiration. I will not tell you. This is by default. It is designed to avoid aspiration. We cannot design the down sparrow unless it must avoid aspiration. If you design and not consider that, you will get defect in a casting, scrap casting. So, right, you understand me? So this is by default. I'm not going to tell you that. Anyway, down sparrow is designed here, down shown in the figure, has been designed to avoid aspiration. What does that mean? B0 equal to B1 equal to B2 equal to B whatever, all pressure throughout, atmospheric pressure throughout. So I mean all time. So and deliver liquid cast iron mold at rate 10 kilogram per second. Rate of 10. This is a flow rate. He said that flow rate is 10 kilogram per second. 10 kilogram per second. We know that flow rate is cubic meter per second or cubic centimeter or cubic millimeter per second. So why it is given here as 10 kilogram per second? Okay, anyway, let's just move forward and see. Then a flow rate is 10 kilogram per second to the sparrow. We deliver here liquid at 10 kilogram per second, not cubic meter, but kilogram per second. Give me the density of the liquid. The liquid density is given. This is the liquid metal density, the liquid of the material that we put here. The density of the liquid material that we deliver here is 800 kilogram per cubic meter. Neglect the friction and orifice effect. So neglect is all to default unless given something else, then friction usually neglected in the sparrow. What is the flow rate cubic meter per second? This is the first question. Then the given flow rate is kilogram per second, and he requests what is the flow rate in cubic meter per second. Then first question, what is the flow rate in cubic meter per second? So given is 10 kilogram per second, and we need to know what is a cubic meter per second. Actually, you see second is same, but here kilogram and here cubic meter. This is a mass. Kilogram is actually a mass, and cubic meter is a volume. What is the relation between mass and volume? Mass equal to rho v. Mass equal to rho v. So if you need to get the volume, you divide by the density. So if you divide here by density, you get cubic meter per second. So actually, let me tell you, rate is given as 10 kilogram per second. We call it m dot. M dot, flow rate, mass flow rate. This is mass flow rate m dot, because here mass. Flow rate meaning time. So mass flow rate is m dot. The relation between mass flow rate and volume flow rate equal to m dot divided by rho. Kilogram, you divide it by density, which is the mass, you divide by density, get volume. So m dot, if you divide m dot, this is the m dot actually. Let me tell you, 10 kilogram per second is the m dot. 10 kilogram per second is the m dot. If you divide m dot by density, this is the density given here, then you get Q, which is the volume flow rate. Volume, not mass flow rate, but volume. So we have whatever we call mass flow rate, which is 10 kilogram per second. Volume flow rate is cubic meter per second. If you have mass flow rate, you divide by rho, you get the volume flow rate. So Q now equal to 10 kilogram per second divided by rho, which is 7,800. Then this one is kilogram per second, 10 is kilogram per second. So this one rho is kilogram per cubic meter, mean cubic meter per kilogram. Then kilogram go with a kilogram, you get cubic meter per second, which is the volume flow rate. So volume flow rate obtained by mass flow rate divided by the density of liquid material. Any question? Right, so this is the first question. Second question, we need the velocity V3 at this point. So how to solve? Here is given dimension are given here. He says that this is the height here, h2, because this is 0.2, this is 0.1, this is 0.2, this is 0.3. Then h1 equal to 100. h3 equal to 100. h3 equal to 100 plus 400 mean total 500. The head of 0.3 is 500. The head of 0.2 is 100. The question is, what is the velocity at 3? What is the velocity at 3? V3 equal to square root 2gh3. 2gh3. G, gravity acceleration, and h3 equal to 500 millimeter. Not 400, but 500 millimeter. 2gh3. This is the velocity at the spiral. The down of the spiral, or the bottom of the spiral, which is the V3. Next, what is the area here? Area 3. What is the area 3? What is the area 3? A3. Actually, we know the flow rate. Q, we know the Q. Flow rate is given. This is constant. All the way is constant. This is a flow rate. Then, as long as we know Q, then Q, we can know that V3, A3 equal to Q. We know V3 and we know Q, then we get A3. So area at 3. Then we need area at 2. What is the area at 2? What is the area at 2? There are a relation between area at 2 and area at 3 related to the head. Then use the relation between area and head. Another way is to calculate the velocity here at 2. There's another alternative way to calculate the velocity at 2 equal to square root to GH2, which is 100. Then you get velocity at 2, and you know the flow rate. Flow rate is constant everywhere. Then you know the flow rate, you can get the area. So either you use velocity method to get the area, or you use the area head relationship to get the area of 2. Let's see the solution. This is the solution. Velocity at 3 here, square root to GH3. You get the velocity at 3. Area 3, Q divided by V3. Because Q equal to VA, then Q divided by Z, and you get the area at 3. Then area at 2 you can obtain directly from relations. Then area at 3 divided by area at 2 equal to square root HC divided by H1. So it doesn't matter what is the name. It means that this is the 100 and this is the 500. This is the head of this point is 100. The head of the other point is 500. It means that square root, this is the head A3 divided by A2. This is the H2, just correct it, H2 divided by H3. H2 is 100, H3 is 500. This 100 and 500. Then you can obtain the area here. This is one way to obtain the area. Someone says that, okay, I can do in another way. Yes, how to do? You get the velocity at 2. How to get the velocity at 2? Square root to GH2, H2 which is 100. You get the velocity here. This is the 1. When you get the velocity here, you have Q. Q is same. Then you can say that A2 equal to Q divided by V2. Then you can also the area at point 2. Any question? Is it clear?
Clear, doctor, yes. Clear, doctor, yes.
Perfect. Okay, let's just move forward. That's nice, actually. This is a nice way, actually. Okay, this is the equation. A3, generally, this is he talk about system and so on and reach to this equation. What is needed? You can see the drawing here. Needed is, he says if the sparrow shown above, HC equal to 80. HC, this is the HC. HC, this one, this head equal to 80, which is head for point 2 equal to 80. H2 equal to 300. H2 is this one. this one equal to 300, mean H1 equal to this one plus this one, which is 80 plus 300 is 380. The head of point 3 is 380. Used to pour cast iron in the mold at rate is 12 kilogram per second. 12 kilogram per second meaning this is m dot. This is the mass flow rate. If you would like to get the Q, which is the volume flow rate, you divide by the density. Density actually is given. Liquid density here is 7,800. Then if you would like to get the Q, then you divide by density, you get the volume flow rate. Then determine the flow rate actually. This is the volume flow rate. Then volume flow rate, you know that 12 divided by this one, you get the volume flow rate. This is the first question. Second question, velocity of liquid metal at point 2. Where is the point 2? You need the velocity at point 2. You know the head, then directly you can obtain this one. And the bottom of the spiral, meaning V3 also, you can obtain by the head. So V2 and V3 can directly be obtained by the head. Diameter of the spiral, 0.2 and 0.3. They get the area and they get the diameter. They get the area, you have the Q. Q already we have from here, then Q equal to VA. We know V here and V here, and you know Q, then you get area here, you get area here, you get diameter here, and get diameter here. Time to fill the cast cavity. Time to fill the cast cavity. This is the cast cavity. We need to know what is the time to fill the cast cavity. This one is given, the dimension of this one is 500, 400, 100. This you get the volume. So the volume can be calculated. We need to know, we know the Q. Q already we know, and we know the volume of the mold. Then you can divide V by Q. Then you get the time needed to fill the cavity. Okay, so here is a solution actually. Then simply you can read it, and this is the finally time to fill the cavity. So this actually is a solution you can apply. This is another two problem, similar. Then please practice. Please by yourself. It is not solved. This two problem not solved. I'm just giving you to practice. Please try to use your hand and calculator and practicing solving this kind of problem. Right. Definitely you can ask me anytime if there are an issue. Next is we need to always be sure that it is laminar, no turbulent flow in the mold. I mean the liquid metal is in a laminar flow, not in a turbulent. We all time concerning about that. We all time even we said that it is avoiding aspiration previously, and we did the design to avoid aspiration, and we maintain velocity at certain level to avoid aspiration, to trapping the gas inside, to avoid porosity in the material, and so on. But there are another way to check. There are another way to check. We call it is Reynolds. We use a Reynolds equation. We use a Reynolds equation to check the condition of the casting. So Reynolds equation says that this is the dimensionless group, dimensionless no units, equal to VD rho divided by zeta. V is the velocity of the liquid. At certain point, if you talk about certain point, velocity, diameter of this point, the velocity and diameter at this point, for example, in a spiral or in somehow, this is the velocity of the point, this is the diameter of the point, this is the density of the liquid metal, this is the viscosity. Zeta is the viscosity of this liquid. viscosity يعني بالعربي يا شباب اللزوجة بتاعة المعدن اللي انت الليكويد ميتال اللي انت بتستخدمه. يبقى دي السرعة، دي الديامتر، ده الدينستي كثافة، دي اللزوجة بتاعة المعدن اللي انت بتستخدمه. ويقول لك الرينولد نمبر دي، الرينولد نمبر لو اقل من 2000 if Reynolds number if this Reynolds number if you calculate find Reynolds number less than 2000 it is laminar, it is fully laminar as you can see here. If this one between 2000 and 20,000, if the value is between 20,000, it is mixed between laminar and turbulent and acceptable. We accept this one also in casting. This one should be okay also. So this one and this one probably is okay. Finally, if it is find, I mean the value here bigger than 20,000, this is a severe turbulent. Severe turbulent mean it is like this, meaning that it is cannot be used, because if you have this condition, then you get turbulent, you get gas trap inside, you get bubbles, you get cavity, you get defect in a casting, this one not acceptable. Let's take an example and see how to apply Reynolds equation to be sure. This is to justify what you had before in the Spiro by using Bernoulli and continuity equation. There are an example. It is a nice example. I hope you just give me your attention here. So let's read together and understand. This is really nice. Let's read it together. A metallic workpiece. This one. Finally, we would like to have this. This is a cavity. This is a cavity. That finally we need to cast this part shown in the figure below. Okay, is to be manufactured or casted by sand casting. Casting is done to pure liquid into the pouring cup. Here we put liquid in a pouring cup, sand mold. It has found that liquid metal flow from the pouring cup into the down spiral with the flow rate is kilogram per second. This is the mass flow rate, huh? No matter mass flow rate, volume flow rate, no matter, we can change from this one to that one and so on, and vice versa. Then this is the flow rate. Mass flow rate is given. Mass flow rate of the liquid is given at the top where the pouring cup lead to the down spiral, the cross section area 75 here. At the top when the pouring cup, this is the pouring cup, right? Pouring cup down to the down spiral leading to the down spiral mean at point one. At point one, it means at point one. Then at the top where the pouring cup, this is the pouring cup leading to into down spiral, meaning here the cross section is 75. Then the cross section area of A1 equal to 75. And length of spiral 18 centimeter. Length of spiral 18 centimeter. Length of spiral or length into spiral is 18 centimeter. Vital viscosity here is given. H is he give you H here. Down spiral. This is the down spiral, not spiral, but down spiral is 18 centimeter. Material viscosity is given. Viscosity is given and density is given. So viscosity here given and density is given. Determine whether this flow turbulent or laminar. The question is it turbulent or laminar? This is the question. Just move forward to the equation. How to do? We're going to apply this equation. I mean, how to think about. Just we're going to apply equation. This is a Reynolds equation. To know if he asks you about that, then we need to apply Reynolds equation. Then finally, we need to apply Reynolds equation. To apply Reynolds equation, then we need rho v. Rho is given and zeta is given. Then rho is okay. In this equation, we know rho. Rho is okay and viscosity is given also. Still, we don't know what is the V and D. We need to get V and D. Right, we need to get V and D here at down at point 2. We need to get V and D, get velocity and diameter at the down spiral here. Then we can apply in the equations, then we can obtain this. Why point 2? Someone will ask why we didn't apply at point 1. No, we have to apply at point 2. Why we need to apply at point 2? Because point 2 is a very important point, as I told you, because point 2 leading to the cavity. The condition here tell me what is going to happen later in the cavity, not point 1. Point 1 is very early, so we are concerning mainly about point 2. We need to apply Reynolds at point 2. So rho and zeta, or the viscosity and density given, we need to get V and D at point 2, right? Actually, area here given and H is given. We don't have H, full H from 0. We don't have the head of 2, but we have H between 1 and 2. Okay, then flow rate we know is given because he gave me flow rate in mass flow rate. Then we get mass flow rate, we have the density, and we have mass flow rate. We can just get Q. Then Q, we get Q, and we get velocity at the top spiral here. Because we have the area here, we have area here, A1, then we can use Q, and A1, then we can just get V1. So V1 we get, then we have V1. We have V1. We cannot apply between 0 and D. Someone said that square root 2G, we need to get the velocity here. Okay, velocity here equal to square root 2GH. H what? H2. Where is the H2? We don't have. We don't have H2. We have here H between 1 and 2. We don't have H2. We have to apply between 1 and 2. Apply Bernoulli equation. This is the Bernoulli equation. We need to apply Bernoulli equation because I don't have the head of point 0.2. Then we apply Bernoulli apply between 0.1 and 0.2. If you apply between 0.1 and 0.2, in case of apply between, then pressure is through, you have to avoid aspiration. To avoid aspiration, B1 equal to 0, B2 equal to 0. Friction we will ignore. He said that ignore friction. Then we'll ignore friction here. Then you have here in the equation H1 and H2, right? H1 and H2, and we have V1 and V2. The H1 and H2, put the reference anywhere. You put reference here or you put reference here. You get the difference is H. Difference between head 1 and head 2 is H. Then it is, you get equation here, square root 2GH plus V1 square. Why it's coming like this? Because here H is the difference between 1 and 2, and you apply between 1 and 2. Here velocity 1 and velocity 2 are considered. No 0. We cannot say velocity 1 equal to 0. We cannot ignore velocity 1. We must consider velocity 1. If you solve this problem, you get square root 2GH plus V1 square. 2GH plus V1 square. So this is the equation obtained here to avoid aspiration. This is the equation. If you apply between 0 and 2, it is 2GH, because V0 is, it is still plus V0 square, but V0 we consider as 0 because it is here, and for simplicity we make it 0, then we didn't consider. But if you consider between 1 and 2, then velocity 1 must be available or must be 0. We know velocity 1. Velocity 1 we know, and we know H is given and velocity 1 given. Then you can apply here, you get velocity at 2. Then velocity at 2, no. If you know velocity at 2 and you know Q, then you get A2. And if you get A2, you get diameter at 2. Then you get A and diameter. Then you apply in Bernoulli equation. Then we find that it is 8,400 something. So it is, you can see here, it is less than 20,000. It is less than 20,000, meaning okay. Actually, we can reach up to maximum 20,000. We don't have to exceed. So this one acceptable. It is between laminar and turbulent, something between laminar and turbulent could be okay. Better to make it laminar, but if it is between laminar and turbulent, it could be okay. This is another way to check about the turbulent and laminar flow. Right. Any question? Right. Fluidity. Fluidity is really very important. We have whatever we call fluidity. Fluidity really is very important. Fluidity means how the liquid flow, smoothly flow. Why we concern about fluidity. كلمة fluidity يا شباب بالعربي يعني السيولة. قد ايه المعدن ده liquid metal اللي احنا بنستخدمه عنده good fluidity. Is it important? Yes, very important. Why? Because if the metal or liquid metal have a good fluidity, it can easily flow to fill all cavity, as you can see. It will be easily flow. If bad fluidity or poor fluidity, what will happen? If the metal have or liquid metal have poor fluidity, then it will be difficult to fill all cavity. Probably stop. Then liquid just move and fill certain area and then stop, solidify. Because it is very bad fluidity, then premature freezing and not filling the cavity perfectly, then you didn't get the cast, you get scrap. Then fluidity is really very important. So what is our target? To increase fluidity. All time our target is to increase fluidity. Have higher fluidity is better. Higher fluidity is better. There are a factor affecting fluidity, which is the viscosity of the material, and definitely higher viscosity, metal with higher viscosity, lower fluidity, surface viscosity of the material, surface tension of the liquid. Higher surface tension meaning difficult to move, fluidity is low. Inclusion inversely affect. Inclusion is inversely affect the fluidity also. Inclusion means foreign material. If the material is not pure, liquid metal is not pure, there are additional or other material in the liquid. It's coming like contamination or maybe oxide or maybe any inclusion is inversely affecting fluidity, make fluidity is poor. Solidification pattern also very important. Solidification pattern, what does that mean? Solidification pattern means that whether you melting a pure material or melting alloy. Pure material have a certain pattern. If you melting alloy have different pattern, definitely if you have constant temperature for melting or solidification at constant temperature better than having range of solidification. This one affect also fluidity. Characteristic of cast pattern and affecting how cast or mold affecting. This is a liquid. This is a liquid. This is a characteristic of liquid metal affecting fluidity. This is a characteristic of the mold itself. Mold itself affecting the fluidity. Like mold design, mold material, mold cavity surface, degree of superheated, rate of pouring, heat transfer. This item is factor affecting also fluidity related to the mold itself. Actually, time is finished. Class time is just finished. I think I have to stop here. Then let me stop